In this short video I'll explain you how to estimate multiple linear regression model in R. So let's get started. So if you remember, by the way, this is the script that I used in my previous video when I showed you how to estimate simple linear regression in R. Now these two lines basically install two packages, ReadExcel and Stargazer package. ReadExcel package helps us to import Excel data into R, while the Stargazer package helps us to present our regression output in a neat and tidy way. So I have installed this so far, and we will just load them. So we click here in row 8 and then run. That's done without an error, so library loaded the package. Next, Stargazer is loaded. So, and now I can import the data and call the data or name the data my data, right? So this is the data directory that I saved the data in. So run, and I have the data stored here now, so I should be able to use it now. So let's view quickly what we have imported. So as before, this is the data set of school districts or schools in California. So these are elementary schools. In Britain, these are obviously primary schools, and we have data for each school. I mean, we have observations of it's not moving. So we have observations of a standardized math score, math test scores, and reading test scores here for each school. And also we have some variables that show characteristics of each school or students' sort of metrics, measuring here. This particular variable here measures the number of students or percentage of students who are still learning English. So here this school, and which school is this? For some reason, okay, here it is. I can move it now. Third school, let's say Thermalito Union Elementary School has 30% of its 30%, that's a massive 30% of its students still learning English. So these students or these pupils are still learning English, or they speak English as a second language. Now this is interesting. 68% of the students are consider them English as their second language. So interestingly, when a student or a pupil is still learning English, doing a math test in English is probably will be very hard, and the same with reading as well. So that's that score may reflect these this sort of characteristic here. So low score, yeah, may reflect this characteristic of the school here. And as you can see, where it is 0% here, for example, so there is not a single student who still learning English basically while studying in school, yeah, there is not a single student. And then the math test or reading score here is quite high, the same with the math as well, compared to this one where the percentage of English language learners is quite high, and the tests and then reading scores are very low for these schools. Now, so now you might have guessed the direction towards which we are going now. We will now try to estimate if in addition to student teacher ratio that we used last time, if the ALPCT or percentage of English language learners affect the math scores. So this is about the multiple linear regression. So we will add one more variable to what we have already got from before, yeah. So let's get started. So before we start, let's write our population regression model here, just for expository purposes. So we have test score. This is our population regression model. Is a function of, so that's beta 0 intercept, beta 1 is TR, student teacher ratio, plus beta 2 LPCT, so percentage of English language learners plus the errors. So this is the population regression model. So we would like to estimate this true parameter value with a beta 2 hat. So this will be the estimate for that parameter, and also this one here. So previously we had this part only estimated. If you remember, we estimated a single simple linear regression model. Now we will gonna add this, and you will see the importance of doing this. Now the benefit or the advantage of doing multiple linear regression is that we can hold whatever we included in the model constant. Sorry. So we can hold whatever additional variables we included in the model constant while looking at the effect in isolation of STR. So we are now controlling for this for the effect of this English language percentage of English language learners. Now what can we assume in advance here? We can assume that if this variable goes up, if LPCT goes up, we can assume the effect to be negative, or if this variable goes up, the test score will go down. So we can expect that as a result this estimate to be negative. Now STR wise, and if you remember, if STR had a negative effect, so we still keep that negative sign here, and the reason is when the class size is larger relative to the teacher numbers, or the teachers teaching the teacher per class, then we would expect larger classrooms to be less controllable, or to be hard to teach as well. So large classrooms, one teacher or few teachers in a large classroom will probably find it hard to teach. So we will now estimate this model in R. Close this. So we have the data loaded. I don't need to attach this, but attaching will help if you're especially plotting the data. Let's do that. Just let's run it. Maybe at some point we will have to plot something there. So for comparison, we will estimate the regression 1. I don't need the summary, or maybe for comparison again. Let me run it just in case. So let's have a look at it. I wanted this video to be shorter, but it's going a bit longer. Now notice this STR score, STR coefficient is negative. It's statistically significant, so keep that in mind. Yeah, keep this in mind now. As we estimate the multiple linear regression, things will change. So let's write the next model. So I will just copy the first model. I could comment here. No, let's not waste time. So reg 2, I'll just name it as a reg 2, as a regression number 2, and STR, let's see, should be there. So this will be now ELPCT, if I remember correctly. Yeah. So let's run this now. So we have output there. So let's have a look at the summary and run the summary as well. What's there now for us? Wow, that's interesting. Very interesting result here. This effect of STR is now, or the coefficient of STR is now less than unity. So it's minus 0.91, and if I go back, it was minus 1.93, almost twice, twice I should say, as high as this value here. So it reduced massively, and it's also not statistically significant at the 1% anymore. It was here, but when we just ran this regression with STR alone, yeah. But then when we added ELPCT, or percentage of students still learning English, we noticed that this is actually a more important variable than this variable, yeah, STR. Than STR, it lost some of the statistical significance here. So there's kind of weak evidence of its importance now, while this variable ELPCT is the main determinant, apparently is main determinant of math score performance, yeah, math test performance, I should say. And interestingly, this I should look at now adjusted R squared, because now we have multiple linear regression model. Adjusted R squared is calculated slightly differently from multiple. Just I mean, the r keeps for some reason r says multiple. It's actually simple r squared. Yeah, this is simple r squared. But when we have more than one variable, then we will be comparing adjusted r squares, or using it as a benchmark to compare model fit. Now the reason is, with adjusted r squares we adjust or penalize the increase in r, usually as you add an additional variable. For in this case, for example, we added LPCT. So as we added, this went up. You see this, it increased to 0.33. However, we did a bit of adjustment here and calculated it should really be 0.32 rather than as high as this number. So there is a bit of penalty. So to reduce the inflation in r squared, there is a penalty in the adjusted r squared. So we're gonna focus on adjusted r squared as a result. So what it means is that, let me just go back. What's this here, or this here? 0.35, or about 4%, let's say. Yeah, so we usually look at r squared here because of singular linear regression model. So almost 4% of variation is explained. So STR just explains almost 4% of variation. But when we added LPCT together, STR and LPCT explained 33% of variation in math score. So that's a large improvement. It's a massive improvement, and is a better model than this simple linear regression model. Yeah, so let's do this. Let's do a quick stargazer output, and then we can then discuss the interpretation of this model in a whiteboard. So I'll call this a stargazer. So we'll take the reg2 here, this model. So we'll take reg2. We'll leave this as text. By the way, last time I mistakenly said this can be PDF, but it cannot be. It can be HTML or text. So if you use HTML, then it will import the output. The stargazer will export the output to HTML. But then we'll keep it as a text so that it prints the result in the console. And let's look at the labels now. Math score is the dependent variable. Now covariates, here we have from before student teacher ratio, that's STR. We also need to add now LPCT. Now don't use underscore here, it doesn't work. You'll get an error message if you use an underscore. So if you remember, LPCT variable has this this underscore, but we shouldn't be using it here. So just keep it as LPCT. So run, and we have some output here. Yeah, this is neater. I can see that I can read this better. So math score is our dependent variable, and our independent variables are LPCT and the student teacher ratio. So we'll export this into our whiteboard, paste, and let's extend this, or maybe increase the font. That's better, but I don't see it. Okay, so I'll have to do a bit of manual correction here. So that needs to move a bit. So these figures in brackets are standard errors, and constant standard error for the constant. This is r squared, adjusted r squared, and then I have f statistic. This f statistic is huge now. Last time it was, I think it was 16. This is a huge value, so statistically significant at a very small significance level even. Right, so let's write this in context now to make it simple to interpret it meaningfully, I should say. So test score now predicted with these results, with this estimated coefficients. So 19, that's negative 0.91 times STR. Now another negative value, and that's 0.57. So that's that done here. This is ALPCT. That's it. This is our estimated model. Now let's interpret. So first of all, this, if you remember, just to remind ourselves, in a simple linear regression model, this estimate was minus 1.93, something like that, yeah, and it's now less than half of it now, yeah. The reason is it looks like STR and LPCT correlate, and when we do not include LPCT when estimating the STR's effect on TS, what happens is that the OLS estimator captures or reflects the effect of LPCT as well. So the effect of LPCT on TS is captured here. So it actually inflates then as a result the coefficient estimate here. Now when we included this LPCT here in our new model, this the effect, it kind of the variable now captures its own effect, and now STR is left with its own effect now. Yeah, so we isolated effects now here in a multiple linear regression model. Here we couldn't do that because we couldn't keep this variable constant, or we couldn't include it in the original model. As a result, this coefficient estimate here is just inflated. So that's the nice characteristic or property of multiple linear regression. Now when interpreting, what we say is that we hold everything else constant, in this case LPCT, and then we can then kind of assess the isolated effect of STR. So our focus has been on STR, if you remember. So STR, student teacher ratio, is now has a lower coefficient estimate, and in this context, if student teacher ratio increases by 1 unit, the test score, average test score, declines by just under unity, or by 0.91. yeah, so that's holding LPCT constant, or everything else constant. So this is the ceteris paribus, or maybe ceteris paribus, depending on where you're coming from. Yeah, so I mean it's kind of a regional pronunciation. Apparently it's different in different regions, but it's ceteris paribus, if I remember correctly, in British English. So moving on now, so this is the isolated effect of STR, or in economics we call this a marginal effect of STR on test scores. So similar interpretation applies here as well on LPCT. So if holding everything else constant, if an English language percentage of English language learners increase by 1 unit or 1 percentage point, the test score will reduce by 0.57 points. So that's the sort of a marginal effect of LPCT on test scores. So this is the benefit or advantage of using multiple linear regression. We are able to isolate or capture, or in more simple words, quantify the effect of individual variables while holding everything else constant, yeah, that we included. So we can hold constant here LPCT only, but we can include more variables. And remember, test scores or school performance may depend on a lot of other factors, like background of a student, or let's say family background, whether they are from rich family, or let's say maybe the support they receive in families. For example, some parents provide more to their kids than others, and in some districts are actually wealthier than others. Yeah, so maybe we'll look at the income. Yeah, let's look at the income, effect of income on test scores while we hold constant STR and LPCT. So to do that, let's go back, and then I will view our data one more time. View data. So these schools, so average income, here it is. So this is the average income in the school district. So that's there's a huge variation though. There's a huge variation. That's interesting, isn't it? So poorer districts will um, most likely will not be able to provide learning materials or technology, I should say, compared to the richer ones. So I can see this district is quite rich, and also it has 0% of English language learners. So it means these are American people or families. Well, even if the immigrants live there, they speak perfect English, so they are not actually, their kids are not learning English. While this district here is almost 70% of the student pupils in this school still learning English. So that means they certainly will not understand much of what's in the test, in the math test, for example, or reading. Yeah. So let's add this variable and then see its effect. See its effect and what happens to our STR estimate. Yeah. Right. So we'll copy this one more time, and we will add plus AVG Inc. So average income. Let's call this third regression, and we will probably need the summary as well. So run. So that's done, and then let's have a look at the result. Wow, that's unexpected. So STR is basically not significant anymore. In other words, student-teacher ratio, when this is more than 0.05, we conclude that the effect of this variable is 0. It doesn't have any significant effect. So student-teacher ratio is not an important variable that determines the test score, in this case math test score. While these two variables that we just included, LPCT and average income, are important determinants, because both of them have statistically significant coefficients. Although this here is slightly lower than before, but that makes sense because now we included something that's important here. This is statistically significant, so it probably captured early this the LPCT coefficient previously. What was it? Yeah, it's probably reflecting the effect of income as well, and well, STR has become coefficient of STR has become a positive, but you can ignore it because now it's not significant anymore. And another important point is adjusted R squared. It is huge. It's almost 62%. Oh well, just over 62% of variation in math scores is explained by this three variables taken together jointly. That's a huge explanatory power. Yeah. So what we can do, we can also drop this variable if we want, because this doesn't appear to be a significant variable, but we will keep it for now, and we're not going to re-estimate the model given the time. But notice this. Just last point to note here is that holding everything else constant, if average income goes up by $1, I guess this is in thousands of dollars, so $1,000, then the test score increases by 1.50 or 1.50 points, 1.5 points in other words. That's a massive increase. So in other words, more resources make big difference to student learning, yeah, people's learning. So higher average income means more resources usually, right? So in schools, school districts where the families are in higher income most likely pay higher taxes. That means the schools are supported with more taxpayer money, so they can buy more technology, learning resources. That certainly has a significant effect. So this is also a policy relevant issue here. So policymakers may want to have a look at this.